Welcome back, my dear students. We'll continue the chapter current electricity. There is a little part is remaining in current electricity. Then we will move to magnetic effects of electric current. That means moving charges and magnetic fields. And let's discuss now. So in today's session, we will be finishing heating effects of electric current, and then we discuss a chapter called moving charges and magnetic fields. Let's start. Heating effects of electric current. If you take a resistance R, a resistor of resistance R, a current I is flowing through this resistor in a time t. According to Joule's law, we know this heat energy produced in this resistor is equal to I square R into T, and heat energy produced by this resistor is equal to V square by R into T. The heat energy produced by this resistor can also be written as V into I into T. Observe this. This is called the Joule's law, right? All these things, Joule's law expressions. Heat energy produced by a resistor. If you carefully observe this point here, there is a term called I square into R. There is a term called V square by R. And there is a term called V into I. What does it mean? So now this is about heat energy. What is this H here? So that is the heat energy. Now I am writing a quantity called P. That P is called electric power, my dear students. So the same power we can also discuss in work, energy and power chapter. There the power is called mechanical power. Here the power is called electric power. Okay, so what is this electric power? And this electric power is equal to electrical energy divided by time. And this electrical energy, I can also write it as the above mentioned heat energy. And this is heat energy divided by time. So if I cross multiply these two equations and carefully you observe, and heat energy is equal to electric power into time. And this equation, let us compare with 1, 2, 3 equation. What is that? Heat energy, yes, H. Power, this part, into time, this one, right? Heat energy is equal to power into time. Heat energy is equal to power into time. So I can write the expressions for the power. Power is equal to I square into R, and the power is equal to V square by R, and the power is equal to V into I. So very important, 3 equations for the power, 3 equations for the heat energy we have discussed right now. My dear children, depends on the question given, depends on the data is available with you. You need to use a particular formula. And so many students ask us what formula to be used for which question. It is so simple and you will understand. Just write the data given, you will understand what formula to be used. If the data is given related to V and R, so if they ask you to find the power, which formula will be used? The data is about V and R, which formula is to be used? Right? So you can use V and R. So directly you can use this formula. Directly I am sorry. Indirectly you can also use this also, because if you know V and I, so you can find I is equal to V by R. I hope you understand. So directly you can use this formula. So P is equal to V square by R, because V and R is given. Indirectly also you can use these formulas, because I value you can find from V and R value. Right? So like that you can use the given data and substitute in an exact formula. All right. Now, let's move again to the another topic, and that is also related to the power itself. Right? Okay. Let's take, there is a resistor R1 and another resistor of resistance R2. They are connected in series. So now a current I is flowing. As they have connected in series, the same current will be flowing through here. Understand? So now what I can write, power is equal to I square into R, if this is the formula I use. When I is constant because series combination, so power is directly proportional to R, right? So what is this P? Electric power consumed by this resistor. Electric power consumed by this resistor. So what can I write from here? So it is P1 by P2 is equal to R1 by R2, my dear students, right? R1 by R2. The same expression goes like this: when two resistors are connected in parallel combination, my dear children. When two resistors are connected in a parallel combination, so now here I can write P is equal to V square by R formula, and V I can keep it as constant because in parallel combination, potential across number of resistors will be same. So that's the reason I can write P is inversely proportional to R. So from here, what can I write? P1 by P2 is equal to R2 by R1. What is P? Once again, I am asking you and I am telling you. What is P there? Power consumed by the resistors. Power consumed by the resistors. Listen everybody. Right? Now, when we move to the next topic related to the same series and parallel combination only. Related to same series and parallel combination only. Right? Listen. So, this series combination is there. Imagine we have connected a potential difference. That means a battery for this combination. And for this combination also we have connected a battery. The question is to find effective power, my dear students. Effective power is equal to effective potential of the circuit by effective resistance. Carefully observe. Here also the same. So if they ask you to find the effective power, which is equal to, so effective voltage of the circuit divided by R effective. Here R effective, how will you find out? R effective is equal to R1 plus R2. Okay, that's what I am writing because of the series combination, R1 plus R2. And here R effective, how you will find out, my dear children? R effective is R1 R2 divided by R1 plus R2, like this. Clear? I hope you understand. I hope you understand, my dear children. Now, let us discuss this formula. Remember, H is equal to V square by R into T. Comparatively, the other two formulas, and this formula we will be utilizing and using more. H is equal to, what is that formula? V square by R into T. V square by R into T. And let me use that formula and tell you some more applications related to your NEET exam or CET exam, or some of the students are writing JEE exam. For them also it will be useful. So very interesting and important application related to H is equal to V square by R into T. We are going to discuss, right? I hope you're ready right now. H is equal to V square by R into T. Carefully observe, if H is constant and V is also constant, my dear children, what can I write the relation here? From here, the relation I can write resistance is directly proportional to T. Resistance is directly proportional to T. And believe me, my dear students, so on this, you may get a question in your final exam, and that much importance is there for this. Alright, and let's move on. See here, I have a heater coil. For example, heater coil. In our houses, we'll be using heater coil. Nowadays, nobody using, but olden days, so many people are using, and before these geysers and all. So there is a resistance R for this heating coil. right? And water is boiling because of this heater coil in a time t1, and there is another coil. Because of this coil, the water is boiling in a time t2. They are not the temperatures. I am not at all talking about the temperatures here. In a time t2, the water is boiled when this coil of resistance R2 is used. When this coil of resistance R1 is used, the time taken to boil the water is t1. Now what happened, you know? Simple question. When the coil is made in series combination of these two, what is the time taken to boil the same water? When the coil is made in parallel combination of the above two heater coils, what is the time taken to boil the water? Simple. Simple. Right? What we have discussed here? Resistance is directly proportional to the time. Why resistance is directly proportional to the time? You may get a doubt. Sir, resistance is directly proportional to time when H and V is constant. Right? So in this case also we are boiling the water. Boiling the water means same amount of heat energy. After reaching to the same temperature only we say the water is boiled. So heat energy supplied is constant, and we are using the same amount of the electric supply. Electric supply involves the voltage applied. So that voltage applied is also constant, right? In our houses, voltage supplied to a particular device is constant. So now H and V are constant, resistance is directly proportional to T. And in this case, resistance is the effective resistance, which is R1 plus R2. That's the effective resistance here. And now this T is equal to T1 plus T2 because resistance is directly proportional to the time. All right, here. What is the expression for here? So my dear students, will you please message me in WhatsApp? What is the expression for this? Everybody should message. Everybody should message. Then only I'll understand whether you're following it or not. So at this point, time is equal to, because the effective resistance here, which is R1 R2 by R1 plus R2, and here time is equal to T1 T2 by T1 plus T2. The beautiful expression you have got. A very important and the beautiful expression you have got, my dear children. Okay, clear, sure. Now the questions will be asked like this. So imagine this is the time 2 seconds and imagine this is the time 4 seconds. In this case, what's the total time? So 2 plus 4. In this situation, what is the time taken to heat or boil the water? So 2 into 4 by 2 plus 4, like that the questions will be asked. Alright, so very important expression. Now we'll move to the concepts and the deeper levels of electric power, right? Deeper levels of the electric power. And let's look at this, my dear students. And there is a bulb here which will have a power rating. What's the power rating here? So let me write, for example, 100 watt, 220 volt. And this is the symbol called the power rating. And this is the expression called the power rating. And this is connected to a voltage supplied, for example, voltage applied is 110 volt. Look at this. So this is called voltage applied, this is called rating power, and this is called rated voltage. So simple. Rated power, rated voltage. So rated power and rated voltage I want to discuss with you now. So what is this rated voltage? See, when you supply 220 volts to this bulb, 100 watt power it will be consumed and it gives the maximum brightness, right? So when you supply this 220 here, this power consumed will be maximum 100 watt and the brightness will be the maximum in case. So when you supply less than this 220, so the brightness of the bulb will be lesser. When you supply more than this 220 here, this bulb will be fused. That's the topic. Now, in this situation, I hope you understand what is meant by rated voltage. Rated voltage is the voltage supplied for the maximum brightness of the bulb, for the maximum power consumed by the bulb. Right? That's a rated voltage, and this is what. So this is the rated power. Now this is the voltage applied. So in this case, power consumed by the circuit, right? Listen here. So power consumed by this bulb, it is not 100 volt, 100 watt, because here we supplied is less than this, I told you. When you supply exactly 220, then 100 watt is the power consumed by this bulb. So in this case, power consumed formula will be VA by VS whole square into rated power. So what is the VA? 110 by, what is VS here? 220 whole square into power consumed. It's 100. 0 gets cancelled and 1 2s are, so 1 by 4 into 100. It is how much, 25 watt is only the power consumed by this bulb. The power consumed by this bulb is only 25 watt. So based on power consumed cases also, the question can be asked. So that is what we will discuss right now. And before we move to that, I just wanted to convey one more important point here. Listen, my dear students. And there is a bulb here. And here is another bulb of power consumed P1 and the power consumed P2 here. And here there is one bulb and there is another bulb, and one is the power consumed P1 and this is the power consumed P2. Simple, students, simple. So these are the bulbs which are connected in series combination. When the bulbs are connected in series combination, the effective power consumed will be equal to 1 by P1 plus 1 by P2. They are like a capacitors. I hope you remember, like capacitors. So here the effective power consumed in the circuit will be P1 plus P2. They are also like capacitors. In resistors, what happened in this case, In capacitors, what happens this case, And now, about the power also, you must know them. Okay? Clear? So, coming back to the next point. So, next point is the most important point, and listen to me, everybody. Here, there is a bulb. Here, another bulb. Listen. So, this is so values also I'll give you. 100 watt, 220 volt, and this is a 50 watt, 220 volt. So this is connected to the voltage 220 volts. Okay. Now here the same concept. 1, 2 bulbs, same. 100 watt, 220 volt, and this is 50 watt, 220 volts, and it is supplied to 20 volts. In this case, the question will be which bulb will glow brighter, right? In the series combination, which bulb will glow brighter? In the case of parallel combination, which bulb will glow brighter? And that's the situation, right? Are you ready? Are you ready, my dear children? So now listen, I'm going to give you a shortcut, and very important shortcut here. Listen, the shortcut is that right. Simple. Sri Lankan Prime Minister. Remember this line, that's it. These problems you can solve. Sri Lankan Prime Minister. What is meant by Sri Lankan Prime Minister here? SLPM. Remember, SLPM. You know what is SL? In series combination, my dear students, remember, in series combination, low power rating bulb will glow brighter. In series combination, low power rating. So this is 50 watt is the low power rating. Yes or no? 650 watt is the low power rating. This bulb will glow brighter. See, simply I am representing. Write your notes properly. Now, in case of P stands for what? Parallel combination. In parallel combination, M stands for more power rating bulb will glow brighter. Simple. More power rating bulb will glow brighter. In parallel combination, more power rating is where? For the 100 watt. So this will glow brighter. Right? Simple. In series combination, low power rating will glow brighter. In parallel combination, more power rated bulb will glow brighter. So I am writing here, will glow brighter. Simple, will glow brighter. So let us discuss moving charges and magnetic fields. Welcome back. Let's start a new chapter called moving charges and magnetism. Let's begin. Moving charges. A moving charge can produce both magnetic field and electric fields. That's important. So that means there is a electric field which is Q into E. There is a magnetic field which is Q into V bar cross B bar. When there is a charge moving like this, it will produce both magnetic field and electric field. Magnetic field is there means magnetic force will be there. Electric field is present means electric force will be there. And those expressions I have written here. That means the net force acting on this is equal to, observe carefully, the electric field plus the magnetic field, my dear students. So this net force is called Lorentz force. No confusions, right? The net force is called Lorentz force. So this F suffix L bar is equal to addition of these two. So Q into E bar plus V bar cross B bar, right? So this is what? The Lorentz force. And in the Lorentz force itself, we have discussed a quantity called velocity selector, my dear students. So this is the velocity selector. I hope you remember. So V is equal to E by B. V is equal to what? E by B. What is E? Magnitude of the electric field. What is B? Magnitude of the magnetic field. So this is about the Lorentz force. Right? In this chapter, moving charges and magnetism, we must understand one important thing. We must understand one important thing. Imagine a situation where there is a current carrying conductor is like this. Right? Always remember right side for this wire. So the magnetic field lines are into the plane. Right side of this line, magnetic field lines are into the plane, and left side for this line, the magnetic field lines are out of the plane, my dear children. Remember, the magnetic field lines are out of the plane. All right? Clear? Very important. And how you got this? How you got this? That is important, right? So we have got this by using right hand thumb rule. What is that? Right hand thumb rule. Here I am not going to discuss in detail what is right hand thumb rule, but I would like to tell you directly. Listen carefully. So this is the current carrying wire, my dear children. Imagine the current is moving in this direction, right? Imagine we are holding the current direction. See, imagine we are holding this current carrying wire such that the thumb is pointing in the direction of current. and the curl of the fingers represents the magnetic field lines. And coming back to this is the direction of current, and thumb is pointing the same, and the curl of the fingers, you see here, right side of this wire the field lines are into the plane, and left side of this wire field lines are out of the plane. Understand? Clear? So that is about the magnetic field lines here. So that is the right hand thumb rule. At the same time, you must understand a Fleming's left hand rule. Fleming's left hand rule. And let's talk about this, because this is very important for the further discussions. What is this Fleming's left hand rule? And already we have discussed this so many times. Shortcut also I have told you. So this is father, and this is mother, and this is child. So what is this F stands for? F stands for magnetic force. What is that? Magnetic force. And what is the other one? M stands for magnetic field. And what is C stands for? Electric current. And very important, this part, this is also called the motion of the positive charge, my dear students. What is that? Motion of the positive charge. And observe here, this is the magnetic force is represented by the thumb. The magnetic field is represented by the forefinger, my dear students. And the current or the positive charge is, motion of the positive charge is represented by the middle finger, my dear students. Alright, so this is what the Fleming's left hand rule. Listen here. So this is the left hand. So this thumb is pointing the magnetic force, and this forefinger will point the direction of magnetic field, and automatically your middle finger will gives you the direction of electric current or the positive charge. Any two directions, if you fix, the other one automatically will come out, and that will be the answer. Understand? Clear? So mostly this is the Fleming's left hand rule is used to find the direction of the magnetic force, my dear students. Is used to find the direction of the magnetic force. Mostly it will be used for that. Okay. Now, and this is what the Fleming's left hand rule will use in the concept like force on a moving charge in a magnetic field. What is that? Force on a moving charge in a magnetic field. A very important concept. From here you may get a question. If you are lucky enough, you may get a question from here itself, right? So that's the reason, focus more, my dear students. So force on a moving charge in a magnetic field, already we have discussed the formula for the magnetic force. What is that? F is equal to Q into, this is what, VB sine theta. What is that? QVB sine theta. What is the theta? Theta is the angle between V and B. That is important. Theta is the angle between V and B. So what is V bar? So motion of a positive charge, for example, motion of a positive charge. Yes, this is V bar direction. So what is B bar? Magnetic field direction. Yes, this is magnetic field B bar direction. So you know this direction and this direction. By using Fleming's left hand rule, you can find the magnetic force direction, my dear students. You can find the magnetic force direction, and you can also use by how to find the direction in the cross product of the vector, you know, and that also you can use V bar cross B bar. If you identify, that will be the direction of the magnetic force. Okay, coming back to this situation where theta can be 0, theta can be 180 degrees, and theta can be 90 degrees, and theta can be other than this any. Right? So let us talk about one by one. Each and every case is important, and each and every case, from each and every case there may be a question, right? So that is why we should be very, very careful while listening to this concept, while studying this concept. There are so many formulas are involved. Everything is important. Okay, and let's talk about one by one. So the first case, 0. What is 0 here? 0 is the angle between V and B. Okay, 0 is angle between V and B. So this is the magnetic field lines. Simple. This is the magnetic field lines. And a quick revision as maximum as possible. The details also we are discussing. We are not sticking on to the only formulas and numericals. No, we are completely revising the chapter. So here, this is the magnetic field direction, right? So what is this V? Charge of a electron or charge of a positive charge, anything. Imagine there is a positive charge which is thrown like this. This is the direction of V bar. So the angle between V bar and V bar is 0 degrees, right? So theta is 0 degrees. The first case, let's say it's a first case. So there is no force acting here because this theta will be 0 degrees, sine 0 will be 0, no force is acting. But the interesting thing is that when force is 0, acceleration is 0. When acceleration is 0, so the body will be moving with constant velocity, my dear children. Body is moving with constant velocity. That is very important. There won't be any deviation in the path, but it moves with a constant speed, right? Or constant velocity. There's no deflection taken by this. So second case is the same charge, positive charge Q is moving in this direction. So what is the angle between V bar and V bar here? Students, what's the angle between V bar and V bar here? So the angle between V bar and V bar is again 0. Angle between V bar and V bar is 180 degrees, but still sine 180 is also 0. 0 into QVB is again 0. So even in the second case also, the force will be 0. Right, I'm writing second case theta is 180 degrees. Look at here, V bar is in this direction, your V bar is in this direction. So theta is 180 degrees, force is 0, theta is 0 degrees, force is 0. So two cases are finished. But the most important part is this, my dear students. Most important part is that. What is the angle? Theta is 90 degrees. So what is this theta is 90 degrees? Listen carefully, everybody. So here there is a magnetic field which is into the plane like this. The magnetic field lines are into the plane in this way. The magnetic field lines are into the plane. So what are we going to do? We are just projecting a charge like this. See here, exactly perpendicular. Listen, the magnetic field lines are moving into the plane like this, inside the board. From here, inside the board, you imagine, inside the board. So now I have a positive charge which is projected like this. See how simple it is. So the magnetic field lines are into the plane. I'm just projecting a charge here. What happens? Perpendicular to each other, right? So when theta is 90, sine 90 is 1, we get force is QVB. What is that? So we get F is equal to QVB. That means a maximum force we get, my dear children. Right? So if you apply this Fleming's left hand rule to find the magnetic force in this case, and this is the charged particle will take a circular path, and that circular path will have some radius r. So mass of the particle is m. With what velocity it is taking a circular path, that's v. And observe carefully, and this is the circular path is uniform circular motion. In uniform circular motion, what happens? That is very important. In uniform circular motion, all scalar quantities remain same. Very important. All scalar quantities remain same. Speed is same. Energy of the particle is same. Right? So, in the same uniform circular motion, all vectors vary. Velocity of the particle moving in uniform circular motion is different at different positions. Acceleration is different at different positions. Right? Velocity is different, acceleration is different, and momentum is different. If that is a vector quantity, that will keep on change because of its direction change in uniform circular motion. So, but all the scalar quantities in uniform circular motions remain same, like energy, like speed, like that. Okay, fine. So F maximum is equal to QVB here. Now this is equal to centripetal force. Any body to move in a circular path, one force is necessarily acting on that. That's a centripetal force, and that centripetal force always acts towards the center. Okay, and from here we can write R is equal to mv by qb. And this mv, I can also write it as linear momentum by qb. And this linear momentum, we can also write it as square root 2m into kinetic energy divided by qb. Right? And this kinetic energy, we can also write it like this. So this kinetic energy, we can also 2m into kinetic energy. In the last class, we discussed q into v, charge into potential. Charge into potential. So divided by QB. Okay. So remember all those expressions, my dear students. There's no point in by hearting these expressions. Each and every formula is important, but no need of by hearting. If you keep on practicing, automatically it will be recollected during your exam time. Okay. So remember all these expressions. R is equal to mv by qb. This mv is linear momentum, and again this linear momentum in terms of kinetic energy, and this kinetic energy in terms of q into v. That's a concept of potential. Potential is equal to work done per unit charge. The same way, kinetic energy is equal to q into potential. Okay, if you take these two, imagine q and b are constant. So the expression you can write r is directly proportional to b, like r1 by r2 is equal to p1 by p2. If they give the ratios, you need to solve a question. Right? So P1 by P2 ratios are 1:2. Then the radius of the circular path ratio you can find out. And see, for example, my dear students, listen carefully. So for example, if this is the situation, these two, same charge, same mass and uniform magnetic field, if you take it, and your R value is directly proportional to root of kinetic energy R. Right? And if the question is given as kinetic energy 1 by kinetic energy 2 is equal to 1 by 16, so then you will get R1 by R2 is equal to root KE1 by KE2. So that is 1 by 16. Root 1 by 16 is 1 by 4. And from here I can write R2 is equal to 4R1. Yes, I hope you understand. So like this basic kind of numericals will be asked, right? So basic kind of numericals will be asked like this. Understand? And so many numericals are given in the notes. You just have a look at it, right? So don't waste much time on that. Anyway, after the classes, you have lot of time with you. You just practice them, right? So whatever the numericals are given during the notes, during the first time when we are learning this chapter, you just go through them. All right. Now, so coming back to this, so there is a time taken by the circular path. This time taken is equal to 2 pi m by qb. And this time period, if you know, and the omega also we can write, that is angular velocity or angular frequency. Angular velocity or angular frequency. Omega is equal to 2 pi by time period. And this time period you substitute, here, you will get the answer. Okay, and one important thing, so T and omega, they are independent of radius of the circular path. Independent of the radius of the circular path, remember. So this is about this case. What is this case? When theta is 90 degrees. So when theta is 90 degrees, we have discussed all these things. Now, my special focus is on this part where theta is not equal to 90, not equal to 0, not equal to 180 degrees, other than this angle. For example, so now this is the magnetic field B bar. Now the body is projected, the charge is projected with a V bar like this. And this V bar is making an angle theta with B bar. So this V bar can be resolved into two components. There is a V cos theta here and V sin theta here. Right? So this V sin theta is perpendicular to B bar. V sin theta is perpendicular to B bar. So this V sin theta component is responsible for the charge to move in a circular path, and V cos theta is the component responsive. This V cos theta is having 0 degrees with the B bar, right? So when the angle is 0 degrees, then the force is 0, body will move with a constant velocity in the linear motion. Okay. And this component is making the charge to move in circular path, and this component of velocity making the charge to make the linear motion. Alright. Is it interesting, my dear students? Okay. Fine. So V cos theta, it's responsible for the linear motion. So whatever may be the situation, time period you can find, time period of the circular path, right? Or radius of the circular path. Radius is equal to general formula. So what is that? mv by qb. But here, what is the velocity? There are two velocities here. In previous case, there is only one velocity. Now there are two velocities here. So, but which component is responsible for the circular path? So that's a v sin theta. So mv sin theta by q. Right? In the same way, time period is 2 pi m by qb. So here time period is independent of the r and velocity. So 2 pi m by qb. Here also the same, 2 pi m by qb. And omega also is independent of the velocity and radius of the circular path. As it is, it will be there. Right? So, but here one important thing you should understand, and that's called the pitch. In one of the years, there was a question based on the pitch even for JEE exams. Right? So, what is that pitch? Pitch is equal to horizontal distance traveled. So, horizontal distance traveled. Listen, horizontal distance traveled for one complete circular path. So, to make one complete circular path, see, simultaneously it is taking circular path as well as the linear path also. So for taking one circular path, what is the horizontal distance traveled? So that is called the pitch. And how to find that pitch? Okay, look at here. So pitch is horizontal distance. Distance is equal to speed into time. So v cos theta into time taken to complete one circular path. So that is what v cos theta into time is 2 pi m divided by qb. Remember this, right? So if you know the different values, you can definitely find the things, right? You can definitely find the things, my dear students. Let's continue the topic called Biotsavart law. Biotsavart law. And there are so many applications in it, my dear students. Let's begin. Number one. Imagine, so this is the current carrying wire. Okay, it's a current carrying wire. From any arbitrary point, imagine the point is this one. At a distance r bar, at a point P, we need to find the magnetic field. Simple. Any current carrying wire we have taken. From this point, at a distance r bar, there is a point P is located. Complete length of the wire is L. A small length element, so that is called dl bar. The small length element, it's a L bar like this, small dl bar, sorry, it's already mentioned. Small dl bar is here. So there is an angle between dl bar and r bar, that's a theta. This is the wire, left side of it, the magnetic field lines are into the plane according to right hand thumb rule. So at this point, the field lines will be into the plane, At this point, due to this element, the magnetic field is dB bar is equal to mu naught by 4 pi I dl bar cross r bar divided by r cube. This is the vector form of Biotsavart law, my dear children. Generally, the magnitude, if you write, that will be dB is equal to mu naught by 4 pi. It's a IDL sine theta divided by r square. So the general form of Biotsavart law is this one. Vector form of Biotsavart law is this one. In the same way, you will get general form of Coulomb's law, vector form of Coulomb's law, general form of Newton's law of gravitation, and vectors form of Newton's law of gravitation. Right? All these are important. Now, let's come back here. So this is the dB, magnetic field at this point due to the small length element. If you integrate this, you will get the magnetic field due to the complete length of the wire at this point. That's B. Right? Now, let's talk about the applications. And the first applications, my dear children. First application. Look at this. There is a long straight current carrying wire. Right? Sometimes they will not mention that it is infinite wire. A long straight current carrying wire they will mention. So that means, so this is the infinite current carrying wire of infinite length. Okay? So this is the current is I. So in this case, at any perpendicular distance r, you know the magnetic field is mu naught I by 2 pi r. Simple. Mu naught value, you should not get any confused. Mu naught value is 4 pi into 10 raised to minus 7 Tesla meter per ampere. So SI unit of magnetic field is Tesla and CGS unit is Gauss. It is denoted with a symbol capital G. And there is a relation between Gauss and Tesla that you need to write it in the WhatsApp and send me immediately. What's the relation between Gauss and Tesla? What is the relation between Gauss and Tesla? 1 Tesla is equal to how many Gauss? 1 Gauss is equal to how many Tesla? That you need to write it and send me immediately. Now, coming back to this. So at this point, magnetic field magnitude is this one and the direction is very important because magnetic field is a vector quantity, my dear children. According to right hand thumb rule, at this point, the magnetic field is into the plane. Right? So you may get it out. Sir, how come you have got this expression? Right? So to know that, you must know the general expression for this one. So what is the general expression? And let me write here. The general expression is, there is a finite wire we need to consider. Right? To get the general expression, finite wire is here. So this finite wire through which the current I is flowing, exactly at the center of it, so at the point P is considered, you know, one end of the wire at the point P is making an angle phi 1. Another end of the wire and the point P is making an angle phi 2. At this point P, the magnetic field formula I am writing here, mu naught I by 4 pi r into sine phi 1 plus sine phi 2. And this is the formula is derived from Biotsavart law only. This is the formula is derived from Biotsavart law only. I hope you have studied Biotsavart law derivation for your second PUC topics, for your second PUC preparation, right? All right, and coming back to this. So this formula, when you apply in our previous case, this is a finite length the wire is having. Here the wire is having infinite length. When the wire is having infinite length, and observe carefully, so this infinite end will form an angle 90 degrees with the point B here. And this infinite wire also will form an angle 90 degrees here. So we have phi 1 and phi 2, 90 plus 90, okay? And substitute here. This is sine 90. How much? So 1. Sine 90. How much? That is 1. Sine 90 is 1 plus 1, it's 2. And here 2 and here also 2 gets cancelled and you get mu naught I by 2 pi r. Is it the mu naught I by 2 pi r, students? Is it the mu naught I by 2 pi r, students? Yes. All right, remember this. Now, one more application. Let me write here one more application. So this is what a wire through which a current I is flowing. Now the point is not lying at a perpendicular distance. Now the point P is lies exactly here. That means along the axis. The point P is lying along the axis. So here, or it may be here also, the point P, both the cases the magnetic field due to this current carrying wire is zero, because there is no perpendicular distance. So in any equation you take it, this is R. In any equation you take it, this is R. Perpendicular distance is not here. When the point of consideration is on the axis, so then the magnetic field will be zero. Then the magnetic field will be how much, my dear children? It's zero. Okay, clear? And one more. Listen. One more. Most commonly asked question, this one. So this is what the infinite wire current is flowing like this, right? So now the point is here. This is the R distance. The point P is here. So we need to find the magnetic field and magnetic field direction. We need to find magnetic field and magnetic field direction. See how interesting it is. And so simple. What I have told you already, this end is making an angle 90 degrees with the point P. The other end is making an angle 0 degrees. That means phi 1 is 0 degrees, phi 2 is 90 degrees, right? Clear? And let us discuss this one. So substitute here. So B is equal to mu naught I by 4 pi R into sine phi 1, that's a 0, sine 0 is 0, sine phi 2, that is 90, sine 90 is 1, and your answer is mu naught I by 4 pi R. Answer is what? Mu naught I by 4 pi R. In this case, mu naught I by 2 pi R. General case, mu naught I by 4 pi R into sine phi 1 plus sine phi 2. And in this case, mu naught I by 4 pi R. Mu naught I by 4 pi R. Magnetic field direction is what? According to right hand thumb rule, my dear students. So our thumb must point in the direction of current. Yes, thumb is pointing in the direction of current. And right side of it, the magnetic field lines are into the plane. Left side of it, field lines are out of the plane. So in this case, the field lines are out of the plane. So that is the magnetic field lines direction representation. The magnetic field lines direction representation. Okay, clear? Now let's move on to the next one. So this is the magnetic field due to a straight current carrying wire. For example, let us bend this wire into the circle, right? Let us bend this wire into the circular form. So that is also Biotsavart law applications only. What we are going to discuss right now, they are also the Biotsavart law applications only, my dear children. Okay. So imagine. So this is the second one, you can say. So this is the current carrying wire I. Here the current is moving in anti-clockwise direction, right? Here the radius of this is capital R or small r also, no problem in it, right? At the center, the magnetic field at the center of this circular current carrying wire is mu naught I by 2R. Mu naught I by 2R, where number of turns are 1. If the number of turns are n, it will be multiplied with n. Simple. Simpler. So there is a big derivation for this. It's not required for us. Mu naught I by 2R into n. Okay. Now listen. So this is magnitude, it's fine. But what about the direction? Students, what about the direction? How to find the direction of magnetic field due to circular current carrying coil at the center? How to find the direction? To get the direction, we have a concept called a clock face rule, my dear students. What is the concept called? Clock face rule. So what does it mean? Clock face rule. It is so simple, Amma. So there are two current carrying wires. Let's imagine. So one is the current flowing is clockwise. The another one is current flowing is anti-clockwise. Right? So clockwise current, let's focus. In the direction of current, I'm just drawing some line here. See one line here. In the direction of current. In the direction of current. So if I'm joining these 2 points, see there is a south pole is there. South pole is formed. This is the short trick, right? So here also, in the direction of current, I'm just drawing 2 lines here, 2 lines here. So when I join these two, and you can see this is the particular face of the coil is behaving as a north pole, right? Clear? This particular face of the coil behaving as a north pole, and this particular face of the coil behaves as a south pole, my dear students. All right? Is it clear? Everybody? So, when a current is passing through a coil, that particular face of the coil behaves as a north pole or south pole, depends on the direction of the current. And here the current is moving in clockwise direction. So that means this particular face of the coil behaving as a south pole. What does mean exactly? What does that mean? South pole, from the south pole or from the north pole, how the magnetic field lines, that is very important. And you know, in the lower classes you might have studied, my dear children, this is what a magnet, bar magnet, north pole and the south pole, right? So from the north pole, how the magnetic field lines will start. And they start from the north pole like this. They start from the north pole like this. They start from the north pole like this. I hope you got it. From the north pole, magnetic field lines will originate, will come out. And the same thing goes here. So we need to curl our fingers in the direction of the current. See here, in the direction of current, if I curl my fingers, then the magnetic field lines will be represented by the thumb. Once again, I am telling you, if I curl my fingers in the direction of current, and the thumb will gives you the direction of magnetic field lines. And of course, you see the magnetic field lines are coming out of the plane. That means it's the north pole. From the north pole only magnetic field lines will come out, originate. Understand? And what about the south pole? What about the south pole? Look at here. So when I curl my fingers in the direction of current, look at here. In the direction of current, if I curl my fingers and the thumb is pointing into the plane. When I curl my fingers in the direction of current, so the thumb is pointing into the plane. When the thumb is pointing into the plane, magnetic field lines are entering into the south. Magnetic field lines are entering into the south. There is a mistake in this diagram, my dear students. Magnetic field lines will originate from the north pole, it's fine. But they will not terminate at the south pole. Right? So south pole is here. They will not terminate, and they will keep on moving inside the magnet also. Understand? So they originate from the north pole and they come to south pole and they move into this magnet. Outside the magnetic field lines moving from north to south. Inside the magnetic field lines are moving from south to north, my dear children. Okay. Okay. Is it clear? Now, coming back to this. So, this is the clock face rule we have finished. And magnetic field at the center of the circular current carrying coil also we have done. Now, listen to one important application I would like to explain here. One important application. So for example, there is a current carrying wire. So this is I and this is I. So number of turns are 1 here. At the center magnetic field is B1. Now this is what is, see here, this is what is turned into number of turns. So this is the magnetic field B2, number of turns N2 is N here. Same wire is made up of N number of turns. Magnetic field at the center now is B2. The relation between B1 and B2 you will get like this. B2 is equal to N square into B1. Remember, my dear students. So if this N value is 4, then B2 is equal to 16 B1. I hope you understand. Simple. There is a wire which is bent into the circular shape of one loop. The magnetic field at the center is mu naught I by 2 R initially. The same wire is bent into N number of loops. That N is 4. The relation between these two is B2 is equal to n square into B1, right? That is a very important, very important, right? Okay, so coming back to the one more situation. So what is this one more situation here? So this is the very important for the advanced level topics. Advanced level means just a little level than the NEET exams and KCET exams. And have a look at it. Very simple. So magnetic field due to a ring. Magnetic field due to a ring. Simple. So there is a ring here whose radius is capital R. You know, from the center at a distance x, there is a point P is located. Alright? So we need to find, simple, we need to find the magnetic field at this point due to this ring. Imagine through this ring current flow is I like this. What is the magnetic field at the point P, right? See, B is equal to mu naught I R square divided by 2 into x square plus R square all to the power 3 by 2. Simple. Simple. So, you know, at the center, that means B at center, it's a mu naught I by 2R, it is fixed. So, because x is equal to 0, even you try, when x is equal to 0, see this x is initially this much. Now when x becomes 0, you substitute 0 here, you get b is mu naught by 2r only. You get b is equal to mu naught I by 2r only. Alright, my dear students? Wow. Now, so the question here, how the questions will be asked in this point? At center, magnetic field is, at the center, the magnetic field is B. See, B. Question is, at what distance the magnetic field will become B by 8? Very simple. At what distance the magnetic field will become B by 8? That's it. Right? Let's move on. Magnetic field at the center is B. At what distance it will become B by 18? Simple. So, at some distance, magnetic field, how much it is becoming? It is becoming B by 8. So, let's write the same. So, B by 8, which is equal to mu naught I R square divided by 2 into x square plus R square all to the power 3 by 2. So, what is this B? So, this I can write it as 2 4s are. Okay. What is this B? So, this B is mu naught I by 2R. Understand? Because B is magnetic field at the center into 4, this 4, which is equal to mu naught I R square divided by x square plus R square all to the power 3 by 2. So, mu naught I cancel. Right? What is left here? So, this is what is left here, just let me write it. So this is 1 by 8r, which is equal to r square divided by x square plus r square all to the power 3 by 2. Right? So this is 1 by 2 cube is equal to r cube divided by x square plus r square all to the power 3 by 2. So if you apply both the sides cube root, if you apply both the sides cube root, what happens? And let me write there, right? Let me write here. If you apply both the sides cube root, so as we are solving this first question first time, so that is the reason I'm solving it in detail. So, if we apply the cube roots, what happens? It will be 1 by 2 is equal to r divided by x square plus r square all to the power 1 by 2. right? Whole to the power 1 by 2. Now we need to square both sides. It's not square root. We need to square both sides. It's 1 by 4 is equal to r square divided by x square plus r square. It's a 4r square is equal to x square plus r square. So it is 3r square is equal to x square, and x value is root 3 into r, my dear students. So whenever x value is, what is the question? At what distance b is b by 18? At what distance? So this x must be root 3 into r. Alright? Clear? If the radius is 2 meter, root 3 into 2 meter, so that means 2 root 3 meters from the origin, 2 root 3 meter distance, when the magnetic field will become magnetic field divided by 8. Right? That's it. Now, one more point here. Listen, students. So this is the next applications we can say. First one about striped current carrying wire we discussed. And the second we have discussed about circular current carrying wire, and this also comes under circular current carrying wire only. Now the third one, magnetic field due to an arc. For example, magnetic field due to an arc, little higher level if we go, so this kind of questions will come. So imagine this is the arc. So this is the center of the circle. If we imagine there is a circle, this is the center of the circle. Current I is flowing here. At this point O, the magnetic field is how much? That's a question. So this is the angle theta. This length of the arc is making an angle theta here. This B is equal to a mu naught I by 4 pi r into theta. See? So many times we have got mu naught I by 4 pi r. So mu naught I by 4 pi r into theta. What is this r? And this is r here. Okay, students. Now this is the magnitude, and what is the direction here? Simple. Direction is simple. So many students have confusions in it. No confusion. See, this is the current direction. So right hand thumb rule you use, and right side of right side of this wire, the magnetic field lines are into the plane. Left side of this wire, the field lines are out of the plane. So that is into the plane. That's it. Remember this one. Remember this. Very, very, very important expression. Magnetic field due to an arc. Now, how the questions will be asked, How the questions will be asked based on all these things. Let's see that. Question is like this. Fine. So this is the current I is flowing like this, current I is flowing like this, and the question is exactly at this point what is the magnetic field? See how simple? Exactly at this point what is the magnetic field? So here there is a magnetic field due to the first wire at this point P. There is a magnetic field due to the second wire at that point P. Right? What is that? So B1 is equal to 0 because this is the magnetic field due to a straight current carrying wire where the point P is lying on the axis. B2. This is the magnetic field due to an arc at this point. At this point angle will be pi, and it is so simple. Mu naught I by 4 pi r into pi. This pi gets cancelled, and the net magnetic field is only B2, which is mu naught I by 4r, and the magnetic field lines are into the plane at this point because for this current carrying wire, this is the right side. Magnetic field lines are into the plane. Okay. So this is how the questions will be asked. This is how the questions will be asked. Right? One more for your better understanding. One more, students. Listen. Right? From here, this is the point P. See? How important this is. Yes. A current I is flowing here, a current I is flowing here, a current I is flowing here. So simple. Right? So what is the net magnetic field at the point B due to these three wires? 1, 2, 3. Due to this, what is the magnetic field? Due to this, you remember, when the point is kept at the end and other end is infinite, we have derived also. Today also we have derived. It's a mu naught I by 4 pi r. And this one, B2, a mu naught I by, just now we have discussed, 4r. See, this is the part, right? 4r. And here, so B3, it's a 0 because the point P is lying on this axis. That is why it is 0. So when you add these two, you will get the net magnetic field. Okay? And let us add it. So the B, net magnetic field, is mu naught I by 4r if you take common. Mu naught I by 4r if you take common. So it will be, here it is 1 by pi and it is 1. So the direction is also very important, I have told you, right? Direction is also very important, my dear children. Here, due to this wire, at this point, magnetic field lines are into the plane. Okay? Clear? And due to this wire also, magnetic field lines are into the plane. So then the net magnetic field is into the plane. Direction is very, 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 very important. Okay? Clear? In this way, numericals and the concepts, revision, quick recap, all the things we can do. And the next class, we will be finishing the chapter, my dear students. All the very best for your exam today in the evening. See you in the next class.